Okay, so we're going to draw the back view of this figure given its orthogonal drawing. So in other words, orthogonal meaning you're perpendicular to it, but it's also this orthospective meaning distance doesn't make things smaller. So if the top view says, okay, so we've got this square, so that's its base when we look down, and from the left and from the right, so in other words, and from the front, so in other words, you've got like this bottom layer, like this. I'm just drawing a isometric kind of drawing. So you've got this bottom layer like this, it looks like, because from the left and the right, you have those bottom four, and from the top, from the front and from the top. So you've got the whole bottom. And then from the left side, so looking this way, you've got this back row sticking up like this. So you've got like this back row here that's sticking up. And then the front row isn't there. So from the right, yep, you've got this back layer taller. From the front, yep, you have, from this view, you have all four taken. And from the top, you have all four taken. So it says draw the back view. So the back view would just be the same as the front view. It would just be, because from the back, you would have this tall part blocking your view. So it would also look like that. Okay, name the bases of the solid. Well, if this is a prism, then the base is if this is a prism, this is a prism, where the bases are a triangle going to another triangle. And so to name the bases are triangle XYZ and triangle WV. Those are the two bases of the solid. Identify the solid. So this one is a couple different things. This is one of the Platonic solids where it's, what is it, a regular, gosh, I don't remember what you call it. It's made of 8 equilateral triangles. And no matter which way you look at it, you get the same. So this square here and then up to a point is the same as this square here up to a point. That's the cool way it's regular. So this would be a regular, I don't know, a regular octahedron is what I would call it. Octahedron. Is there a better name for it? Or what's it called? Okay, yeah, just had to Google it just to make sure. But the reason I said octahedron is this is a polyhedron. Just like a polygon, we name them by like a pentagon for 5 sides. So gon, and then hexa means 6. Gon means sides, so 6-sided thing. Same thing here, the hedron means faces, like the Hydra, the Greek mythology that has all the heads and the faces, right? So this means lots of faces, and then this means 8. So I just counted, and this had 8 faces, and this just happens to be a regular octahedron. So regular octahedron. It's one of the Platonic solids. So interesting. Okay, so how many faces does an icosahedron have? I honestly don't have any idea. I'm going to have to look that up on the interwebs. Good golly, silly question. So an icosahedron, I just looked it up. That's a 20-sided or 20-faced polyhedron. Just a vocabulary word, nothing crazy critical thinking there. It's, again, one of the Platonic solids, so it's just a memorized thing. It's 20 equilateral triangles in this like soccer ball looking thing. Okay, draw a net for the solid. So I'm going to cut it here and flap this down. And then I'm going to cut it here, and I'm going to flap that triangle down. And then I'm going to one time cut it along this top edge, and I'm going to flap these two sides down. So I have in the middle, I have that 2x5 that was already on the bottom. And then what I did is I flapped down and flap on each side. So on this side was another 2x5, and on this side was another 2x5. And then I flapped down the two bases. So this was that bottom that we started with. And we flap down this 2x2x2 equilateral triangle, and up here a 2x2x2 equilateral triangle. So that's the net for this shape. So you could draw that up there if you want. Okay, so find the surface area of the solid. Okay, so now we're looking at the separate pieces here. So the way I would do this is I would say, okay, well, we have one base, so the surface area is one base, plus, and then we have the lateral area of the, I don't know, let's just call it a box, or you call it the prism, okay? And then plus the lateral area of the pyramid, right? So we're not doing the top of the prism, and we're not doing the bottom of the pyramid. Those are covered. Another way to do this is just add up. I'll do it in another color really quick just to show you as possible. So you could also say the surface area equals prism plus pyramid and then minus two bases, because the top of the box is covered, and same thing, the bottom of the pyramid is covered, so we have to take away those two bases. That ends up being the exact same as what I did over here. So we have the base plus the lateral area of a prism is perimeter times height, and the lateral area of a pyramid is 1/2 perimeter times slant height. So here's what we're dealing with our formula. Okay, I'm going to zoom in. I'll switch to blue and I'll plug this in. So the area of the base is 8 times 4, plus the perimeter is 8 plus 4 plus 8 plus 4, all times the height. The height is the distance between the bases, so that's the 3 there. So times 3, plus, when we have 1/2, we just did the perimeter, it's 8 plus 4 plus 8 plus 4. And then times the slant height, which they give us, is root 21. All right, so I'm going to erase this. Remember, the slant height is along the surface, perpendicular to that edge, and it goes right down the middle because we're dealing with the right pyramid here. Okay, that is a weird 3 they give us. Why would they give us that 3? It's different on the two faces. Oh, it's because this is an 8 and this is a 4. So we cannot use this 1/2 perimeter times slant height because we have different faces. That only works when we have a regular polygon on the bottom. So good thing we noticed that bottom is a rectangle. So instead, we have to add up two separate triangles here. Okay, that shortcut does not work. Good thing we caught it here. So we have 2 area of one triangle plus 2 times the area of the other triangle. So here we have 2 times 1/2. The base is 8, and the slant height is, or the height of that triangle is 3. And then plus 2 times, and then we have the area of this triangle on the other side is 1/2. The base is 4, and the slant height is root 21. Okay, so this one here, that and that cancel, so we get 24, plus that and that cancel, 4 root 21. So that's, maybe I'll color code it. So I'll change these ones to, what color? Let's do, how about pastel pink? Okay, and then changing my pen color to that color, I'll show you really quick. That was talking about this face right here that had a height of 3, and there were 2 of them, one in the front and one in the back. And then the orange was talking about these. So they're 2 separate triangles, but it's a mirror image because the base is rectangular, so you have 2 copies of each of those. That's why we said 2 times the area of the triangle. All right, so let's add it up. We get, this is 32 plus, what's that, 12 and 12, so that's 24 times 3, or 72, plus 24, plus 4 root 21. So adding these together, that's what, 104 plus 24, so that's 128. So we get the surface area is 128 plus 4 root 21. Okay, so this plan wouldn't have worked here because we don't have regular pyramids. We can't use that little like shortcut idea there. All right, so let's keep going. Whoa, that was a good problem. Find the lateral area of a triangular prism with a right triangular base with legs that measure, Before we go on to number 7, I just want to actually go back a step. So the real reason we couldn't do the area using the normal pyramid area, which is like surface area equals base plus 1/2 perimeter times slant height. This would still work for a prism. This is what we're going to do here when the base isn't regular. But for a pyramid, we have a different slant height on each side if the base isn't regular and the pyramid isn't right. So if we don't have a right pyramid where the point is directly above the center of the base and the base is a regular shape, then we don't have the same slant height on each face, so we can't use this formula. That was the reason up here. As soon as I saw there was a 3 here and a root 21 here, I went, we can't use that formula. I had to break it apart. So that was the reason, just to be clear. Okay, so let's go to the next one. Find the lateral area of a triangular prism. So we have a triangle and triangle with a right triangular base. So we have a right triangle going to the same right triangle like this. All right, and it says the right triangular base with legs that measure 2 and 3. So we have a 2 and 3 legs of that right triangle and a height of 7. So there's our right triangular prism. I didn't do dashed lines well in that drawing. Okay, so the surface area would be 2 bases plus the lateral area, or 2 bases plus perimeter times height. Although it's saying just find the lateral area, so we are not going to find the area of the 2 bases. So we just need perimeter times height. So the lateral area is perimeter times height. We already know that's 2 plus 3 plus whatever the hypotenuse is, times the height of the prism itself, which is the distance between the bases, or 7. And so all we need to do is find the hypotenuse. So I will go 2 squared plus 3 squared equals c squared. That's 4 plus 9, or 13, is c squared, or root 13 is the length of the hypotenuse. And so this is plus root 13. So that ends up being 5 plus root 13 times 7, or in other words, 35 plus 7 root 13. And then you can punch that into a calculator. Okay, find the surface area of the prism. Okay, so the total surface area, let's switch colors here actually. So the total surface area is 2 bases plus the lateral area, or in other words, 2 bases plus perimeter times height. So the distance between the bases is 20, so we already know that. We know the hypotenuse here is 10. So now we just need to find this other leg. Well, that's just a 3, 4, 5 triangle multiplied by 2, so 6, 8, 10. So I know that other leg there, that right triangle, is 8. And so the area of the base would be a triangle, so it's 1/2 base times height. And that's a different height than the height of the prism itself. Okay, so here we go. So the area of the base is 2 bases, 1/2 times 6 times 8. All plus the perimeter of the base, 6 plus 8 plus 10, times the height of the prism, which is 20. And then it's just arithmetic, right? So the 2 and the 1/2 cancel. So we get, it's 48 plus, and then these add up to 24 times 20. Times 20. And so we get 48 plus 480. So that's 528, not 4. 528, yes. All right, let's switch colors. So use a right cylinder, so it's standing upright. So we have a cylinder base. We have a right angle here as it stands up to a top, all right? With a diameter, so the diameter all the way across, 96.4, and a height, 58.9, round to the nearest tenth. So find the lateral area, find the surface area, and then question 11 is something totally different. Okay, so let's find the lateral area first. Well, remember the total surface area is 2 bases plus the lateral area. Or in other words, 2 bases plus, that's a plus sign, perimeter of the base times height. Or in this case, it's 2 pi r squared plus the perimeter, 2 pi r, times the height. So it's just saying find the lateral area for the first one. So here, the lateral area is perimeter times height, or 2 pi rh. The diameter is given as 96.4, so we divide that in 2, so we get 2 pi radius is 48.2, and that's times the height, which is 58.9, which is exactly equal to, just pull out my calculator, Wrong calculator. There we go. So we have all right, sorry, 2 times 48.2 times 58.9. So that's exactly equal to 5677.96 pi, or approximately equal to 17,837.8. Okay, and then it says find the total surface area. So it's just that same thing, and then so it's lateral area plus 2 pi r squared. That's it. So again, we just add that in. We go, okay, well, it was originally, so that's equal to the 5677.96 pi plus 48.2 squared pi. Right? Yep, just double checking. Okay, so 48.2 squared plus the 5677.96. So that's exactly equal to 8001.2 pi, or approximately equal to times pi. Whoa, that's not a pi. There we go. 25,136.5. Okay. Now it says if the height of the right cylinder is multiplied by 4 and the radius remains the same, what happens to the lateral area? So if the height of the right cylinder is multiplied by 4, but the radius remains the same, well, you have the old lateral area, right, was just from up here, it's 2 pi RH. So it's saying if we keep the radius the same, and we replace the h, so I'm going to erase the h, and we go, oh, we multiplied that by 4, so we get 4h, right? Well, then let's see. That's now equal to, and then we just pull out the 4, that's 4 times 2 pi RH, right? So that 2 pi RH we already have was the original lateral area, so this just goes 4 times the lateral area. So it is multiplied by 4, right? That's what happens to the lateral area because you multiplied one dimension by 4. If you were to multiply both dimensions by 4, then you'd have a 4 times a 4, or 16 times the lateral area. But since only one dimension got multiplied by 4, and it's one term of multiplication, we could just pull that 4 right out front, and it's the same exact number as before with an extra times 4 in it. So it gets 4 times as big. All right. Let's go on to the next page. Okay, so let's find the lateral area of this first, right? So in general, the whole surface area of the shape is going to be one base plus the lateral area, or the area of this regular polygon, so 1/2 apothem times perimeter, plus, and the lateral area will be 1/2 the perimeter of the bottom times the slant height. In general, a lot of the work is going to happen on finding the area of the regular polygon. So first, let's find the 1/2 perimeter times slant height. So that's 1/2 the perimeter is, and we got to zoom in here. There's 1, 2, 3, 4, 5, 6 sides. This is a hexagon. Okay, so we have 6 times. I just had to double check. I had a hard time counting. So we have the perimeter is 6 times 12. The slant height is given as 13. So we have, let's say 1/2 of 6 is 3. So we have 3 times 12, that's 36 times 13. What? So that's 360 plus 330, so that's 3, that's 90 plus 18. So 450, 468 maybe? Okay. Or if I did the arithmetic wrong, it was this right here. All right, and then find the surface area to the nearest tenth. So now we just have to find the area of the base to add to that lateral area. So the area of the base, it's a regular hexagon. Let's go off to the side here. We have a regular hexagon of side 12. And so we have the area is 1/2 apothem times perimeter. And we already know that's 1/2, whatever the apothem is, times 6 times 12. So we already know it's the 1/2 in this multiplies to be what, a 3 times 12 is 36. So we have 36 times the apothem. We just need to find out what that dang apothem is, okay? So we do that in our triangle by cutting it up. Remember, only in a regular hexagon, that 360 divided by 6 gives us these 60-degree angles, and they're congruent isosceles triangles, so we end up getting 60, 60, 60. So this is each one of these is an equilateral triangle of side length 12, 12, 12. So if I go down here, then I get 12, 12, cut the base in half is 6 and 6. We can either use Pythagorean Theorem or 30, 60, 90 triangles to get that the height is 6 root 3. So the apothem there was 6 root 3. All right, so we go back over to find the surface area. Well, the base is 1/2 apothem times perimeter, and that's equal to 216 root 3, and that's 1/2 of 12 is 6, and 6 times 6 times 6 is 216. Yep. And so we add that to the original, and we get that's 216 root 3, and then plus 468. All right, 14 is a separate question. It says, if the length of each side of a cube is tripled, what happens to the surface area? Well, let's just come up with an example. Here's x by x cubed. So the surface area of this is there are 6 squares, and each square is x squared. Okay, well, if we triple each side, now we have 3x by 3x by 3x. Okay, and so the area of that is 6 times, and each face is 3x times 3x. And so that's 6 times 9x squared. And so what we end up getting is the surface area is now 9 times 6x squared. We had the 6x squared was the original. So if it's x by x by x, the original cube we started with had a surface area of 6x squared, whatever the side length was. And now for the next one, we tripled each side length. And what we ended up getting was that same 6x squared multiplied by 9. So it ends up getting multiplied by 9. Now the big picture here is that since we multiplied both dimensions by 3, we ended up getting, the formula here was 6 times side times side, right? Because each side's a square or rectangle or parallelogram, so it's base times height. So what we ended up getting is 6 times, and each of these was multiplied by 3. So we got 2 copies of that 3, so this ends up being the original 6 times side with 2 extra times 3's, or in other words, 9 times the original surface area. Okay, that's the big idea for 14. All right, let's go down to 15 and 16. Use a right circular cone with a radius of 7 and a height of 8. Okay, whoa, I always forget to do that curve at the bottom the first try. So here's a right cone, so right meaning that the height is, or the apex, the top point, is right above the center of the circle. So it says the radius is 7, and it says the height is 8, and it says find the lateral area. So again, it's breaking up separately. So the total surface area is 1 base plus, and then the lateral area, or 1 base plus 1/2 circumference times the slant height. So the lateral area here is the 1/2 circumference times slant height, or 1/2 2 pi r times slant height, or pi rl is a shorthand way to say it. And so we don't have the slant height, so super common is we need to find the slant height here using Pythagorean Theorem between the height and the radius. So this is, just zooming in here, over here we're doing 7 squared plus 8 squared equals L squared. And so that's 49 plus 64, that's 113 equals L squared. So L is equal to root 113. So going back over here, we get that the lateral area is, well, the radius was 7, so it's pi RL. So there's the pi R, and then the L is root 113. Okay, and then it says find the total surface area. Well, the total surface area is just the base plus the lateral area. And we already have the lateral area, so all we're adding to it is a pi r squared. And we know the radius is 7, so that's 49 pi. So we add that base of 49 pi to the lateral area, which we already had was 7 pi root 113. Okay, 17 says, find the surface area of this frustum of a cone to the nearest tenth. Well, the big idea here is we could complete this, okay? So we go, okay, well, let's complete this. Whoa, that was a pretty good completion there. And then we have some extra height here. So what we're going to end up getting is the surface area is the bottom base plus the littler base. I don't know, let's call this 1 and 2 just to separate them so they're not actually the same variable. And then I'm going to do plus the lateral area of the big cone minus the lateral area of the small cone. Right, so that's what I'm going to do. Here's the big base. Okay, that's a circle. Plus small base. Got it. Those are 2 parts of the surface. Done. And then for the rest of it, I'm going to find the total lateral area of the big cone. That's all the way around. Then I'm going to subtract the lateral area of the little cone. And that'll give me the downward bottom portion of the lateral area of the big cone. Okay, so this is easy to start. So pi big R squared plus pi little r squared plus the big is 1/2 and then times the circumference, so 2 pi big R times big slant height, so we'll call that, I don't know, L2, and then minus 1/2 circumference, 2 pi R, so that's a little r, times little circumference, 1. All right, so we're going to have to find these slant heights, but otherwise this is just the big radius is pi 4 squared, plus the top one is pi 2 squared, and then plus the 1/2 and the 2 cancel out, and we get pi times the big radius 4 times, we just need to find the big slant height, and then these cancel, pi times little radius times little slant height. So all we're looking for are the 2 slant heights. That's it. Well, the big idea to find those 2 slant heights is that we have a right angle here and a right angle here, and this whole triangle here shares this angle and a right angle, both the small and the large. So we get 2 similar triangles. So I'm going to call this missing dimension H. And so what we've got here are 2 similar triangles. We've got in H into 2 is similar to H plus 6 and 4. And so we just set up a proportion and go, well, gosh darn, what's that missing height of the top part of the cone? So we go H is to H plus 6 as 2 is to 4. Cross multiplying, so I'm just making sure H is to H plus 6, yep. So 4H, and we could have simplified this to be 1/2 if we wanted, equals 2 times H plus 6. So 4H equals 2H plus 12, not forgetting to distribute. So subtracting, we get 2H is 12, or H is 6. So let's check if it worked out. 6 is to 12 as, yep, okay. So that means this was a 6 here. We could use Pythagorean Theorem here to find the 2 slant heights. So the smaller slant height is 2 squared plus 6 squared equals hypotenuse. So 4 plus 36, so 40. So this one's root 40. And we could simplify that to be root 4 root 10, or 2 root 10. All right, and then this one is just twice as big. So we know that. Or we could do a 4 and a 12. But I'm just going to double it because it's a similar triangle times 2 sides. So this one's 4 root 10. Okay, let's go back to our problem. So here we go. The bigger one was 4 root 10. And the smaller one was 2 root 10. All right, so there we go. We got 16 pi plus 4 pi plus, and this is 16 pi root 10 minus, and this is 4 pi root 10. And so what we end up getting for our final answer is 20 pi, and then plus, and we had the 16 pi minus 4 pi, so we have 12 pi root 10. Cool problem. That was a challenging one. All right, let's go to the next one. Okay, so now we got two parallel planes intersecting these spheres in circles D and E, and DC is 6. So it's not labeled in the picture, but that's 6. And find CE. Well, the big idea here is really if we looked at a two-dimensional slice of this, like if we cut a plane straight down that passed through all three of these points and both of these points, we just shoot straight down. What we really have here is a much simpler image. We have a circle with a chord going across, and its distance, or it doesn't say its distance to center, it says this is 6. And then we have a parallel plane, so this line's parallel to this one. And then it says this distance here we don't know, and this is 4. And then those are intersecting, so this radius is obviously the same as this radius, right? So that's the information that we kind of have. But then there's more information. Because this is a circle and this is a circle, that means the radius in both directions is the same. So that means this is 4, and whatever the radius of this circle is the same as this radius. So this is congruent, and if it goes through the center and cuts it into congruent, then that means it's a right angle. Same thing on the bottom. Radius of 4 in both directions means that chord is bisected. So going through center and bisecting chords means that's a right angle. Okay, so now we can just use Pythagorean theorem. It's given to us that the radius of this top circle was 8. So we could say, oh, this is a 6, 8, 10. So the radius of our overall sphere is 10. So I'll do that in pink here also. So the overall radius is 10, which means overall radius of the sphere here is 10. And then we just have a Pythagorean theorem problem of this is 4, this is 10, and we're looking for length CE. And so I'll call that B. So we have 4 squared plus B squared equals 10 squared. So 16 plus B squared equals 100. B squared 84. So B is root 84. Which is the same as root 4, root 21, or 2 root 21. Okay, next one. Write a formula for the surface area of a hemisphere in terms of pi and the radius. So this is a little tricky, right? Because there's two possibilities, not in this problem, but in general. So if we have a hemisphere, since we have the base exposed, we have two separate things. We have the surface area is the base plus 1/2 the surface area of a sphere. And that's because the base is an exposed portion of this hemisphere. Now in the next problem, when the hemisphere is attached to something, that base isn't exposed, so we don't count it. So in the next problem, it'll just be half the sphere, because we're kind of looking for like just the lateral area almost. All right, so anyways, moving on. Here we get the area of the base is pi r squared, right? Here's r. And plus 1/2 the area of the sphere is 4 pi r squared. So that's 1/2 times 4 leaves us with 2. So we have it's pi r squared plus 2 pi r squared, or in other words, 3 pi r squared. So the surface area of a hemisphere standing alone by itself is 3 pi r squared, just because you have that exposed base with it. All right, next one. Find the surface area of the solid to the nearest foot. Okay. Now in this case, we're going to add it up in pieces. I'm going to say the total surface area is 1/2 the surface area of a sphere, no base added, plus this is the lateral area of a cylinder, and then plus the base, right? Only one base, because the other base on this side is covered up. Okay, so now we've added up. There's 3 separate pieces here. If I were to color code these, why not? We have all the time in the world. Whoa, I undid it. So lateral area cylinder plus 1 base. Let's color code it. So the blue is the half cylinder, and then we'll do orange. So this is orange. And then finally, let's do pink. And the pink is this base down here. So these 3 separate areas are what add up to the total. All right, so now let's just figure it out. So we have 1/2 of 4 pi r squared, plus the lateral area of a cylinder is perimeter times height, plus the base, which is pi r squared. So this is 2 pi r squared plus 2 pi rh, because that's the perimeter of the base, plus pi r squared. Okay, so the total here, if I were to combine just the two like terms before plugging anything in, is 3 pi r squared plus 2 pi rh, and then we're just plugging in numbers here. So the radius is 6 and the height of the cylinder is 22. So this is 3 pi 8 squared plus 2 pi 8 times 22. So that's 3 pi 64 plus 16 pi times 22, which I'm not going to do that double-digit multiplication in my head. Let's get a calculator. That's 64 times 3 pi plus 16 times 22 pi. So that's 544 pi, which you could totally approximate. Okay. Find the, it does say to the nearest square foot. So let's times by pi. So we get that's approximately 1709.0. All right. Oh, it's the nearest square foot, so we don't need the 0.0, just 1709. All right, next one. Find the surface area of the solid to the nearest square foot. So this is really the very same as the last thing, except instead of a circle, it's got a regular polygon. So the surface area, again, is the lateral area of the pyramid on top, right, plus the lateral area of the prism, and then plus the one base. So we're going to have to figure out that base, but let's do it here. So we get the lateral area is the perimeter of the base, 1/2 perimeter of the base times the slant height, plus lateral area of a prism is perimeter times height, plus the base, which, we're just going to have to figure out what that bottom is, but it's 1/2 apothem times perimeter because it's a regular hexagon. So we get 1/2. This is 6 times 8, because the perimeter of the base, there's 6 equal sides that are each 8, times, we're going to have to find the slant height, plus the perimeter of the base is 6 times 8, times the height of the cylinder is 10, plus 1/2, we don't know the apothem, but the perimeter of the base is 6 times 8. All right, so all we really need is what's the slant height and what's the apothem. That's all we don't have from our problem. All right, so up top, we go, well, the slant height here, we know the height is 6, and the slant height goes to the middle of a side perpendicular, and that's, oh my gosh, forming a right triangle with the apothem. So we have the apothem and the slant height are connected. So as soon as we find one, then Pythagorean Theorem, we could find the other one. So all we need to do is find one of the two. Well, we're going to find the apothem, because we have, this is a regular, hexagon? Let's count. 1, 2, 3, 4, 5, 6. It is a regular hexagon. So in a regular hexagon, we have, this is a side of 8. We split it up into triangles. We get that the central angle, divide 360 by 6, is 60 degrees. We get each of these is 60. And so only in a regular hexagon do we get an equilateral triangle. That's 8 by 8 by 8. And so to find the apothem, we cut that down the middle. And we get the middle gets split into 4 and 4, 60, 30, 30, 60. And so this apothem in the middle here, you could use 30, 60, 90 triangles, you could use trig, you could use Pythagorean Theorem. You end up getting it's 4√3 because it was similar to a 30, 60, 1√3, 2 triangle multiplied by 4. Okay, so the apothem was 4√3. So we go back over here and go, that was our apothem. And then we're looking for the slant height. So now in green, we could go, oh, well, up here, we know that. Or let's do it on the right here. We know that 6 squared plus the apothem squared equals the slant height squared. And so we know 6 squared plus the apothem, which we just found, is 4√3. Squared is L squared. So that's 36 plus 16 times 3 equals L squared. So that's 36 plus 48 is L squared. So that's 70. So that's 84. equals L squared. So L is root 84, or root 4 root 21, or 2 root 21. Okay, so we go back over here and we put in a 2 root 21 for the slant height, and then we could clean this up a little bit. So the first one is the 1/2 and the 2 cancel, so we get 48 root 21 plus, that becomes 48 and 10, so 480 plus, and then that's that cancel give us a 2, so we get 48, so 96 root 3. I think that's it. Okay, so up here we get 48 root 21 plus 480 plus 96 root 3, and then you could oh my gosh, wait. It said find the surface area of the solid to the nearest square foot. Do not include the area of the base. Why would you do that? Okay, anyways, they said don't include the area of the base. So just cancel that part out. We are not doing the base. I don't know why they did that, but sure. So the surface area not including the base is that, just because it said so in the instructions. All right, I'm going to pause here and I'll come back in the future. All right, so now we're on chapter 13 here. Find the volume of a cube with a 5-meter edge. So that's this, a cube where every side is 5. So the volume of that is just a prism, base times height, where the base is 5 times 5, and the height is 5, or in other words, it's 5 cubed. And so we get 125 cubic meters. Okay, so find the volume of this. I see this as a prism, so I see this as volume of base times height, where this funky looking shape on the front is the base, and then the height is the distance between the two bases, which is 2. So I see the height is 2. Now I just have to find the area of that base. So I see the base as 2 rectangles. One rectangle that's 10 by 8, and then that carries over. This is a whole 10. And then we have on the left, we have 8 is up here, total of 12, so this is 4. And then with the 3, so this is a 4 by 3 rectangle on the bottom. So the area is 3 times 4 for the smaller rectangle, plus 8 times 10 for the bigger rectangle. That's the entire area of the base shape of the prism, times a height of 2. Or you could have seen it as 2 separate prisms. Like here's a prism 3-dimensionally, and then separate color. Here's a separate 3-dimensional prism. You could have done it like that. I just like doing it as one big object. So 12 plus 80, that's 92 is the area of the base, times 2. So that's 184 cubic centimeters. Okay, find the volume. So again, it is volume equals base times height. We have the height is the distance between the bases is 19. So again, the complicated part is what's the area of the base. So off to the side, we've already done this problem a couple times, or more than a couple. We have a regular hexagon where sides are 2. Just counting, that's a hexagon. Okay, so if we cut this up, again we get isosceles triangles, each with 2. This is 360 divided by 6 is 60, or you just remember by now that we end up getting these equilateral triangles. So the area of the base is just 6 of these triangles, and then we just need to say, well, what's the area of an equilateral triangle with sides of 2? Well, we cut any isosceles or equilateral triangle in half. That gives us a 1 and a 1, and a 60, 30, 30, 60. So that's similar to 1, 2, root 3, or it's not even similar, it's actually congruent to our little pocket triangle. So this height is root 3. So we have 6 triangles, and each triangle is 1/2 base times height. And so each triangle's base is 2, and height is root 3. So we have 6 times, and the area of one single triangle is root 3. So the area of the entire base is 6 of those triangles, or 6 root 3. So we go back over here, and it's 6 root 3 times that. So that would be, what, 120 minus 6 is 114. So that would be 114 root 3. And then units, because we're doing volume, is inches cubed, because both of those were in inches. All right, let's do the next one. Volume of a cylinder is, so it gives us the volume, and that's telling us the volume. And the height is 6. Okay, so that's the height. Find the length of the diameter of the cylinder. Okay, so we know the volume of the cylinder is just base times height, or pi r squared times height. We're given that the volume is 96 pi, and we're given that the height is 6, so we have equals pi r squared times 6. Well, now we just need to find the diameter. So let's start by finding the radius. So we're going to divide both sides by 6 pi. We end up getting that's, what, 16, I think? Yep, 16 equals r squared. So r is plus or minus 4, but we only take the positive number because it's a radius. And so if the radius is 4, that means find the length of the diameter. So the diameter is 2 of those, or 8. So we have, and it was in meters, so diameter equals 8 meters. All right, and then Sam is filling a rectangular pan with liquid from a cylindrical can, okay? The can is 3/4 full of water. Determine whether all of the water will fit in the pan and explain. Okay, well, the volume of the whole thing is equal to base times height, or pi r squared height, or pi 3. Now, it's hard to see, but it's saying this radius right here is 3. So pi 3 squared times 7. So that's pi times 9 times 7, or the volume of the whole is equal to 63 pi. And then it says the volume of the water is equal to 3/4 the can, okay? And so 3/4 times that whole can of 63 pi. 4 doesn't go into 63, that's a bummer. So we just get this big number, so 189 pi over 4. So that's the volume of the water. And then the question is, will that fit in this? Okay, well, the volume of the, what do they call it, a tin? Oh, pan, a rectangular pan. So the volume of the pan is just 2 times 8 times 6, right? So any rectangular solid, just length times width times height. So this is 16 times 6, or 96. So the question is, what is 189 pi over 4, and will it fit in the 96? Okay, so calculator. We could approximate it ourselves, but let's just do it. So 189 times pi divided by 4. This is equal to, or around 148 ... And so will it fit in the pan? No. It has too much volume. Too much volume. Okay. Because the water is 148-ish. Yeah, we're rounding 108.4. And that would be in inches cubed. And the volume of the pan is also in inches cubed, but it's 96. Gosh darn dang, it would overflow. Okay, find the volume to the nearest tenth. Let's do it. Let's do the first one. So the volume of this is just volume of the bottom, which is 6 cubed, plus, and then the top is 1/3 base times height. So it's 1/3, the area of the base is 6 squared. We don't know the height, we have to figure that out. So it's 6 cubed plus that. Now all we need to do is figure out the height. So here what we have is, from the center of the shape down, we're looking for that height. We know that this edge here is 6, and then we're looking for this diagonal length. Well, the diagonal length there, let's look at the bottom square, right? So down here, just for sake, so we have a 6 by 6, and we're looking for this length here, just to get our right triangle going, okay? So if we connect this all the way across, this is a 45-45 triangle because it's a right angle square. So isosceles, these two the same and a right angle. So then that means the whole diagonal is 6√2 because it's similar to our 1√2, 45, 90. So if the whole diagonal is 6√2, that means this length up here is 3√2, or half of it. And now all we need to do is do Pythagorean Theorem to find out if this edge is 6 and this diagonal length is 3√2, then what's that height? And so let's do it. So 3√2 squared plus height squared equals 6 squared. So that's 9 times 2, or 18, plus h squared equals 36. Oh my gosh, and h squared equals 18. So h is √18. Or √9, √2, or 3 root 2. Oh, that's cool. It ended up being a 45, 45, 9 triangle as well. So going back up to our formula here. Oh, I shouldn't have done that right below where I was working. Let's just move it up to here. Okay. So anyways, over here, the height that we got was 3 root. Whoa, I was writing in eraser. 3 root 2. So changing colors because that just hurts the eyes. We got 216 plus 1/3 of 36 times 3 root 2. Well, the 3 and the 1/3 cancel, so we get 216 plus 36 root 2. And that's all in centimeters. Okay. Oh, I skipped number 6. What the heck? I went out of order. I apologize. Let's do it now. Okay, the height of a regular octagonal pyramid is 12 centimeters and the apothem of the base is 4. Okay, let's do that one really quick. So octagonal says the apothem is 4 and it's regular. Octagonal, yada yada, and the height is 12, and we're trying to find the volume, okay? So the height up to the top is 12, and we need to find the area. Well, the volume is 1/3 base times height, and they give us the height, so it's 1/3 whatever the area of this base is times 12. So all we need to do is find the area of a regular octagon. It's like so often, that's the difficulty in these problems, right? Okay, so let's find the area of a regular octagon with 4. So we have octagon. I'm going to do 1/2 apothem times perimeter because we already have the apothem. So it's 1/2 4 times perimeter, and all we need to do is find the perimeter. So in this regular octagon, we cut up 360 divided by 8, and we get each of those is 45 degrees. Cut it in half, so each of these is 22.5. We know that the apothem is 4, so the right triangle we end up getting is apothem of 4, this half of a side, x right here, and then an angle of 22.5. So x is solved by tangent, so tangent of 22.5 equals x over 4. So multiplying by 4, we get x equals, just double checking, yep, x equals 4 times the tangent of 22.5. Okay, and then how many of those are in this octagon? Well, 2 of them make one side, and there's 8 sides, so there's 16 of those x's. Okay, so the perimeter equals 16 of those x's, so the perimeter equals 16 times 4, 64. Tangent of 22.5. And so we just plug that in. So the area of the base is 1/2 apothem times the perimeter, or 64 tangent 22.5. And so the 1/2 and the 4 cancel for a 2. So we get the area of the base is 128 tangent 22.5. All right, so going back up, our entire volume for this was 1/3 base times height, and we got our base. And so our total volume is 1/3, 128 tangent 22.5 times a height of 12. And the 1/3 and the 12 cancel to make a 4. So 4 times 128, double checking in my head, is 512. That's what it is, 512. So the volume is 512 tangent 22.5. Okay, so that was number 6. 512 times tangent of 22.5. All right, let's do number 8 now. Okay, so 8 here, we have 2 separate volumes. This is the volume of the cone, 1/3 base times height, plus the volume of the cylinder, base times height, or in other words, 1/3 pi r squared height plus pi r squared height. And these are 2 different heights. Let's call them height 1 and height 2. All right, well, we're given that the height of the cylinder is 8, and then the total is 13. So that means the leftover height here is 5. Okay, so let's just plug in our numbers. So if we have the volume of the cylinder, that's 1/3 pi 2 squared times the height of the cylinder, 5, plus pi 2 squared times the height of the, oh, I said cylinder, I meant that was the cone, and then times the height of the cylinder, which is 8. So that's it. So we have 1/3 of pi times 4 times 5 is 20, plus, and then this is pi times 4 times 8. So that's 20/3 pi plus 32 pi, or 32 pi would be 96/3, right? 3 times, yep, okay, pi plus 20/3 pi, and so that would be 116/3 pi. Perfect, okay. Let's do the next one. Oh, the frustums. I like the frustrum. So we have to complete this, and then we go, well, the volume is volume big minus volume small. And so we're just missing some length. So let's connect this and go, well, we have the 3, we have the 6. We know these are right angles because it's height. So we got a couple different possibilities here. One is you drop this down and go, well, this is 3. And so that means this is 3 out of the 6, right? And that's because this was a rectangle on the left. That's how we knew that 3 on top drops down to the 3 on bottom. And so then this triangle over here is a 3, 4, 5. So that's a 4. This is a 4. And then we just do, well, the top triangle that has a 3 here is similar to the entire triangle, which has, let's call this top x. So then this is x plus 4. And over here, the whole bottom is 6. And then we have, I don't know, some piece of this is 5. So I don't know, let's call this y. Not that we care what it is, but y plus 5 then for this whole length. Okay, so we just need to know the height, right? Because it's 1/3 base times height, and we have the radius, so we just need the x. So let's set up a proportion here. X is to 3, as x plus 4 is to 6, cross multiplying, not forgetting that this is a package. We get 3x plus 12. So subtracting, we get 3x is 12, or x is 4. Okay, so erasing that x there and putting in 4 if you want to double check that it works out. 4 is to 3 as 4 plus 4, 8 is to 6. Yep, that's a 4 to 3 ratio. It worked out. So now we just plug in our volumes. So let's go back to, I don't know, green. So 1/3, the area of the base, pi big R squared times big height, minus 1/3 pi small radius times small height. So that's 1/3 pi 6 squared times 8 is the big height, minus 1/3 pi, and then the small radius, 3 squared, times small height, 4. Okay, so that equals, I'm just going to multiply it on the calculator. So 6 times 8 divided by 3. So that's 96 pi is the big one, minus, sorry. And the 1/3, one of the 3's cancels. So we get minus 12 pi. So 96 minus 12 is 84 pi. There we go. Shooby-doo. That's good. We don't have a lot of room for these problems, okay? Let's do it in a different color. All right, so again, we're just doing the volume. All the units match. So the volume for 10 is volume equals 1/2 volume sphere plus volume cylinder plus volume cone. So that's 1/2 4/3 pi r cubed plus, and then this is base times height, or pi r squared height, plus volume of the cone is 1/3 base times height, so 1/3 pi r squared height. Okay, and then let's see what we have. I think we have all the numbers. So 1/2 and 4 cancels out, so we get 2/3 pi, and then the radius is 2, so 2 to the 3rd, plus, and then for the cylinder, we know that the radius is still 2, so pi 2 squared times the height of the cylinder is 8, plus, and the cone, same radius, so 1/3 pi 2 squared, and the height of that we don't know yet, but we know the height of the hemisphere is 2, and we know the height of the cylinder is 8, so that's a total of 10 so far is taken up, so that leaves 5 left over. So the height of this piece is 5, so we put in a 5 there. Okay, so just bringing it up here, that's 2/3 of 8 So 8 times 2/3 is 16/3 pi, plus, and then 4 times 8, that's 32 pi, plus, and then 1/3 times, and 2 squared is 4, so that's 4 times 5 is 20, so 20/3 pi. So just doing the fractions together, we get 36/3 pi plus 32 pi. Whoops. And so that's 12 pi plus 32 pi. So that's 44 pi. Very cool. I like how it worked out nicely. All right, so last one on this page. Let's do number 11. All right, so a hemisphere has a radius that is 33 centimeters long. Okay, so hemisphere, that's a half a circle. Ooh, that was not the best drawing. So it has a radius of 33. Find the volume to the nearest tenth. Okay, so the volume is just 1/2 volume of the sphere. There's no tricky, like which surface, anything. Volume's much easier. So it's just 1/2 4/3 pi r cubed. So it's 2/3 pi r cubed. And it tells us that's 33, so it's 2/3 pi 33 cubed. So the thirds cancels out with one of the 33. So we have 2 33s left, and then times an 11. Okay, so that's 33 times 33 times 11 times 2 that's a lot of pi. So that's 2, 3, 9, 5, 8 pi. And that's the exact answer, or you plug it in and get an approximation. Whew, that's a lot. And then the units there would be centimeters cubed. Oh, and centimeters cubed and inches cubed. The main thing for all of these is just making sure that the units match. So whatever units you end up getting, just look at the picture, and as long as everything's in the same units, it doesn't really matter. Okay, let's see. The radius of a sphere is multiplied by 4. How many times greater is its volume? Well, it's going to be 4 to the 3rd power, because if you enlarge a one-dimensional thing, then the three-dimensional thing gets 3 copies of that multiplied together. Oh, look at this. I have this zoom box sitting there for this video. So let's look at this. The radius of a sphere is multiplied by 4. Well, let's actually find it. So the volume of a sphere is 4/3 pi r cubed. And then let's say in a different color, we say, well, we have volume equals, and now we've changed what? Well, the 4/3 is still the same. That's the formula. Pi, that's the same. But the only difference is, what's the radius cubed? The only difference that we've changed is we've multiplied that old radius times 4. What? So the rest of the formula is exactly the same. It's still the same value of pi, still the same old radius, just with that extra copy of 4. So multiplying this out, we get this is 4/3 pi, and then 4r times 4r times 4r is 64 r to the 3rd. And so rearranging that, we get that that's equal to 64 and then times 4/3 pi r cubed. So the only thing that we added there was this times by 4, and then it gets cubed. So now we have 64, and then we just pull it out front. And so it was the same old radius being the same old formula there. So that's exactly the same as the old volume. And so that's 64 times the original volume, the volume OG. Okay, so we get how many times is the greater is the volume? 64 times greater. All right, a cone is 9 centimeters deep. That is deep. Okay, sure. I guess it's just upside down, so they're calling it depth. Sure. So that's 9, and then, whoo, gotta knock at the door. Okay, sorry. So a cone is 9 centimeters deep and 4 centimeters across the top. So I guess that's a fancy way of saying diameter. A single scoop of ice cream, 4 centimeters in diameter. I had to read that sentence. There was a comma there. I missed that comma. 4 centimeters in diameter is placed on top of the cone. So I'm guessing on top means half inside, half outside. If the ice cream melts into the cone, determine whether the melted ice cream will fit in the cone. Ooh, groovy. Some real world applications here. This is the sort of thing you would do when purchasing an ice cream cone at the math store. Okay, let's figure this out. So we're just seeing, is the volume of the sphere or volume of the cone bigger? That's it. Better question is, to what height would it fill? Ooh, that's an interesting question. Anyways, volume of the sphere, 4/3 pi r cubed. You're given the r, right? The diameter is 4, so radius is 2. So 4/3 pi 2 cubed. Let's zoom in a little. This is sphere. And so that's 8 times 4. That's 32 pi thirds is the volume of the sphere. And volume of the cone is 1/3 base times height, or 1/3 pi r squared h. So that's, and what's the h is 7, I think? No, 9. And so it's 1/3 pi 2 squared times height, 7. You can already tell the difference. But anyways, let's go. So it's 4 times that, it's 28 pi over 3. Ha, ha, what's going to happen? It's going to overflow. So overflow, right? So too much ice cream. Okay, and that's because here's the ice cream and here's the cone. Oh, so sad. Okay, next one. Determine whether these two pyramids are congruent, similar, or neither. Ooh, that's a fun problem. Okay, determine whether these are congruent, similar, or not. Well, are the numbers all the same? No, so they are not congruent. So all we need to do is say, are they similar? Well, equilateral triangle on the bottom, is that similar to equilateral triangle? Yes. Scale factor is 5 to 8. So all we need to check is the only other measurement in the entire shape the height of it, right? Because it's a regular triangular pyramid. So we know the bottom is a regular polygon, it's a regular equilateral triangle. We even know the ratio of those. The only question is the height proportional also, or is one taller and skinnier and one shorter and wider? So we're just checking, is that 5 to 8 ratio the same as the heights, which is 4 to 6.4? Is that the same ratio? So cross multiplying, we get 32 equals 32. Check, they are proportional. So yes, they are similar. Similar 5 to 8 ratio. So in other words, if we multiplied everything in this triangle by 8/5, we go 5 times 8/5 and we get 8. We go 5 times 8/5 and we get 8. We go 5 times 8/5 and we get 8. And then we go 4 times 8/5. That gives us 32/5, which gives us, just dividing, that's 6.4. Just double checking. And sure enough, that's 6.4. So every single length times 8/5, or in a 5 to 8 ratio. Similar. The ratio of the volumes of two similar solids is 1 to 2. That's the ratio of the volumes. Okay? Find the ratios of their surface area. So basically what we have is the ratio of the sides. And then that ratio squared is the ratio of the areas. Any 2D areas, so surface areas. And then the ratio of the sides to the third is the ratio of the three-dimensional volumes. Okay, so that's what we have. We have the ratio of their volumes is 1 to 2, or 2 as a scale factor. You can write it as 1/2. I'm going to write it as 2. Okay, so we have the ratio, let's call that sides. The ratio of their sides cubed equals 2. So the ratio of their sides is the cube root of 2. Okay, well then we take that value and we plug it in here and go, well, the ratio of their areas is just that squared. So the ratio of their areas, I don't know why I put a line there, ratio of their areas is equal to the cube root of 2 squared, or in other words, 2 to the 2/3 power, which is around, so cube root of 2 squared which my calculator says is 2 to the, in parentheses, 2/3 power, 1.587 ... So that's the ratio. So it used to be 1 to 2. Now it's 1 to 1.587 ... Okay, next one. Volumes of two spheres are in the ratio, I'm switching colors, are in the ratio 8 to 27. The radius of the smaller spheres, okay, so if the ratio of their volumes is 8 to 27, then we take the cube root of that to get the ratio of their areas. So the ratio of their radiuses, of any one-dimensional length is the cube root of the ratio of their volumes. Okay, so the ratio of their radiuses is 2 to 3. That's the cube root of 8 over 27. So, and then it says the radius of the smaller is 30. So we have 2/3 equals 30 to the big radius. So just cross multiplying, we get 2r is 90. So the big radius is 45. So that's 45 inches. Okay, dilate the cube by a scale factor of 1/2, then graph the image under the dilation. Well, dilating the cube by a scale factor of 1/2, I'm assuming they mean about the origin because they don't say the center of dilation. So what that means is every point gets multiplied by 1/2. So this point was on the axis, but now instead of being 1, 2, 3, 4, it's 2. Okay? Instead of going 1, 2, 3, 4 up, we go 2 up. Instead of going 2 over, so here's the 2, and then all the other points on top too. So now it's over here be the other point. This one would be diagonal like this, 2. This one would be 2 by 2. This one would be right here, 2. So here's the 2 by 2 by 2, right? So that's it, and you could label all of those points in terms of x, y, and z, but that's it. Just says graph it. But yeah, by a scale factor of 1/2 means everything is half as far away from the origin. So that just shrinks the size of the cube back towards the origin. But based on the center of dilation, the scale factor of 1/2 just means the end size, but the center of dilation would say where would it end up being, because it ends up going like outwards from the center of dilation like this, and then to a bigger one. And then it keeps going to an even bigger one. So the center of dilation is really important. I don't know why they left that out here. Oops, there's my center. And so it's like a flashlight growing and growing or shrinking and shrinking towards that point. Okay, the center of a sphere is at that point, and one end point of the diameter is at that point. Find the coordinates of C, the other end point of the diameter. Oh, well, that's like the midpoint formula. So it's just saying, in 3D space, I have a point and the center, find the other point. So in other words, this is the midpoint of them. Or another way to say it is whatever I did to get to here, like say at plus 2x's, then I just do the same plus 2 again. It's just the idea of an average. So that's the way I'm going to do it. So let's see, which is the center? The center is this. So this is the midpoint. And then one endpoint of the diameter. So I'm just going to go, what did I do to get from here to here? And then I do that again. So I went from 7 to 5, so down 2. So I go down 2 more, 3. And then I went from 5 to -2, that's down 7. So I go down 7 more, -9. And then I go down, or I went up 2. So I go up 2 more, 10. So 3, -9, 10. You could have used the distance formula. You could have used the midpoint formula. There's lots of different ways to do this. Okay, so find the distance between these. So it's the same distance formula we used. It's just Pythagorean Theorem, but in 3 dimensions. So let's do it. Ready, set. So difference between the x's. So 2√3 minus 3√3 squared, plus the difference of the y's, 1 minus -2 squared, plus difference in the z's. So that's, doesn't matter the order, but I chose the top one first. So √2 minus 2√2 squared. Okay, so that's equal to the square root of 1, so -√3 squared plus And then 1 minus negative 2 is 1 plus, so that's plus 3 squared, plus negative root 2 squared, that's a negative sign. And so that's equal to 3 plus 9 plus 2, or the square root of 14. So it said find the distance, square root 14. All right, an airplane at an elevation of, whoa, was this the last problem? Hey, look at that, or second to last, I mean. So an airplane at an elevation, that gives us a lot of space to work down below. So an airplane at an elevation of 1 mile is 20 miles east and da 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 da. Okay, so let's draw a picture of this. I'll do it over here. So it is, here's a point, and we're 20 miles east and 70 miles south. Okay, and then a second airplane, and it's 1 up. So if I were to label this, I go, it is 20x, it is negative 70y, and it is 1 elevation, like towards the camera here. So 1 off the ground, you could think about it. All right, and then the other point, the second airplane, is at an elevation of a half, and is 50 miles west. So here we're 50. Oh, that's not a point, but 50 left. And 25 north, so here's 25 north, and it's 1/2 off the ground. So this point would be negative 50, it would be positive 25, and it would be 1/2 off the ground, like towards the camera floating. And then find the distance between 2 airplanes. So this is, again, that Pythagorean theorem in 3 dimensions. So we're just saying what's the difference in all the dimensions from here to here. So it's the square root of, well, x direction was 70, right? I mean, you could subtract, but the x dimension difference was 70, plus, this is delta x, means difference in x, and then the difference in the y's was, we went down 70 and we went up 25, so that's a total of 95 is the difference in y's, and then plus the delta in the z value, or the heights, was 1 mile versus 1/2 mile, so that's 1/2. Was their difference squared. So it's just the Pythagorean theorem. And so that's square root of, weesh, we got to figure that out. So that's 70 squared plus 95 squared plus, and then the difference in altitude is almost negligible, but plus that 1/2 squared is just plus a 1/4, right? That's 1/2 squared. So we end up getting, this is exactly equal to the square root of 13925.25, or approximately 118, so 118.01. Okay, and that's miles, because all of those are miles. Cool problem, just 3-dimensional. Okay, so a molding machine produces 4 centimeter cubes of plastic. Very cool. So 4 centimeter cubes of plastic. 4 by 4 by 4, all in centimeters. The volume of molten plastic needed to produce these cubes is actually 11% more. So we just take that volume, and that's 4 cubed, and then the volume needed, though, is that volume, so 4 cubed, and then we add 11%. So you could either go, what's times 11%, and then plus the original 100%, or a nice clever shortcut, which works out, is go, if we started with 100% and added 11, we then have 111%, or in other words, we multiply it by 1.11. Okay, and then it says, so that was the extra, we need 11% more. Find the amount of molten plastic needed to produce 100 cubes. Okay, so we simply go, the volume needed for 1 is this, and then times 100 cubes. So the volume needed is 4 cubed times 100 for the cubes, and then whatever your method of saying add 11%. So the easiest way is to go times 11%, which is 0.11, and then we add it to the original, but that's 1 whole plus 0.11, so that's the same as multiplying by 1.11, okay? That's the shortcut version. So that's 100 times, 100 times that is 111 times, and this is 64, so 64 times 111 is 7,104 cubic centimeters. Okay. And then, oh, we need in milliliters for some reason. Find the amount. It never said anything about milliliters, but sure. So that's also equal to 7,104 milliliters, which is the same thing as 7.1. Yeah, it doesn't even ask, but 7.104 liters. So just about a little over 7 liters of molten plastic is what you need. Cool problem. Okay, you guys, that was it. Woo! Hope you enjoyed the entire course.